good news on the newspaper page. Love and tradition of the grand design. Some people say it's even harder to find. Well, then there must be some magic clue inside these gentle walls. 'Cause all I see is a tower of dreams, real love bursting out of every scene. Days go by. It's the bigger love of the family.
I don't know how to do any of this trig yet. What? I don't even know what a 10 is. Oh my. Andreas! Wake up! We gotta get this trig done, dude. It's due tomorrow.
Alright, so what do you need help with?
So, I have these two problems.
Wait, hold on. Can you pass me a pencil?
What? Where's it?
I said a pencil.
Sorry. Hold on, pencil. Hold on, chill out. Oh, found one.
Alright, so it's simple SOHCAHTOA, alright?
Why would I need to suck a toe to solve math?
No. It's an acronym. Basically stands for sine opposite over hypotenuse,
Okay.
cosine adjacent over hypotenuse, and tangent opposite over adjacent. That's relative to the sides and the angles.
So then this problem right here is just asking to solve for x using
Sine.
so.
Or so.
Sine.
So how you would set it up is sine 38 equals opposite over adjacent, which is x over 25.
Okay.
And then you would just solve for x. You
Okay.
move 25 over here.
How do you do that? You multiply both sides?
Yeah. Then x would just equal 15.39. See? See how we did that?
So wait, but what do you do after this? You just plug in sine 38
Times 25. Yes.
Okay.
Okay. Now we move on to this question. Just tangent.
Okay.
Adjacent or opposite over adjacent. So we put tan 50 equals opposite over adjacent, so x over 20. We move 20 to this side, multiplying. Then x equals tan 50 times 20. So x would equal 23.84.
Okay. So basically what you did down here is the exact same thing as up here, just using 10.
Yeah.
And you're just going to repeat the same thing over here, I'm guessing?
Using cosine.
So then, you just got to plug, once you get x by itself, you just plug whatever's left into the calculator.
Yes. Okay. So how we set this up is cos 45 equals adjacent over hypotenuse.
Okay.
So x over 16, move 16 to this side. So x would equal cosine 45. So x times 16. So x would equal
Ricardo,
11.
you wanna play some games?
Oh, yeah, dude. Why not? Dude, those new characters look really cool, dude.
Yeah.
I'm really glad I left Andreas to do the rest of that trig,
And no one likes trig.
to be honest.
Yeah,
You know what's
for real.
really cool?
What?
Scale drawings.
Yo,
dude.
for real. What kind of scale drawings though?
What? Well, I actually stayed up really late last night. I was looking at some houses.
Yo, me too. I was up till like 4 a.m.
And I didn't fully understand exactly what a scale drawing was last night. So that's why I was trying to look for some more examples. And I saw so many stuff about rates, ratios, and proportions. dimensions, all that type of stuff.
Dude, there's so much stuff like going into a house. So hard to
Real,
build.
dude. What do you usually like to look at?
Like really big houses, like 4-story houses. It's crazy, like what kind of
The
materials
structural
they gotta-
integrity,
Yeah,
dude?
for real.
Dude,
Dude, they got to use all types of different steel and stuff because the wood's not strong enough.
I know, bro.
It's crazy.
I wish we could look at some right now, dude. To be
Yo,
honest.
you want to?
Yeah, dude. You got an example?
Yeah, dude. My mom does architectural drawings all the time on
She
houses.
has
and stuff.
CAD drawings on her
Dude.
computer, right?
Tons of them.
Dude, let's go, man. All right. Oh my god, dude! I can't wait to see what this drawing's skilled at.
Dude, I found a drawing. Dude, excited.
Yo, dude, look at all these scales.
Dude, it's crazy, right?
What is
Dude,
this?
what I was told is like every quarter inch is like a foot, so this thing's huge in real life.
Like almost as big as this house.
Dude, yeah.
So like, what type of house is it?
Dude, I don't know.
Yo, this is pretty cool, dude. Is this the inside of the house?
Yeah, that's the inside. Dude, I think this shows all the electrical and stuff.
Dude, scale drawings really show exactly how to build a house.
Dude, what if you tried to build a house without this stuff? Is that the upstairs?
Dude, I think it is.
No, dude, it's the basement.
It's crazy. Oh, you know what I think is really interesting?
What?
Positional tolerance layouts showing minimum and maximum separation calculations for given tolerances.
Dude, you like that too?
Yay!
Why are you even looking at scale drawings, dude? Let's go look at that. Yo, we've looked up all these examples on the computer, and I still can't figure out what positional tolerance layouts showing minimum and maximum separation calculations for given tolerances are.
Oh, really? Actually, I know somebody who knows positional tolerance layouts showing
Really?
minimum and maximum separation calculations for given tolerances.
Who?
Andreas knows how to do that stuff.
Dude, where's he at?
Dude, I don't know, bro. We should. Andreas!
Did somebody ring the dingster?
Yo, Andres, can you explain this to us?
Well, I mean,
We found
it's-
this calculation online.
don't feel bad. It's a bit of a complicated concept. Basically, what it is this something's ability to be farther away from its designated location. So, basically, something with the tolerance of 0.3 millimeters can be 0.3 millimeters away from its designated location while still functioning. So, on this example that I drew right here, this is this is 1 unit up and 1 unit to the right. You would use this formula to find the positional tolerance of this object.
So, like, say it was a gear or something.
Yeah, it would be 2 square root of 2 would be its positional tolerance.
So that's how far it could work away from it.
yes, basically.
So, for example, if it's something were to mess up and it moved, if it were still within that range, it would still work.
Yes, but that wouldn't qualify as messing up.
Oh, well, like, yeah, okay.
If something
That's
were
what
to
you
go
mean.
outside of that range,
Then
it
it'd
would
be
stop
broke.
functioning.
Okay, alright, I got you. That's pretty interesting, dude.
Yeah.
I've been looking at this book for a little while, and to be honest, how exactly, like all the gears that are inside of them and stuff, like, how is it that they turn so fast and stuff? Like, how do gears work?
It's all about ratios.
Like, what?
Like a lot of teeth to a little bit of teeth.
Like, an example, like, maybe, like, 8 teeth. If one gear had 8 teeth and was turning something that had 4 teeth,
Yeah.
how would that work?
So like the first gear, if it turns 1 time, the second gear is gonna turn 2 times.
So
think-
that's speed. 'Cause
yeah,
it'll go
that'll
so the
be-
faster.
yeah, because it's going faster.
So it'll make whatever it's making work go faster.
Yeah.
So for example, like in a car, what would something with gears turn? Like the wheels or something?
Yeah, the wheels.
So then when you press down on the gas pedal, the gears will turn faster and faster because of the teeth.
Yeah.
Oh, that's pretty cool. What about torque? Because I'm seeing a lot of stuff about a torque in here, and to be honest, I don't know what that means.
So like torque's like turning power.
So is it the opposite kind of with the teeth or what?
Yeah. You need a little bit of teeth to a lot of teeth.
Yo, that's pretty cool. I don't know. I've been reading this book for a while, and I'm getting pretty tired.
Yeah, me too.
I think I'm gonna go take a nap.
Yeah.
SOHCAHTOA trig ratios inverses. The trig all work. That trig's gotta do the trig. Gotta do the trig, dude. All right. So what? All right. So what's the difference between the regular ratios and the inverse ratios? 'Cause we gotta get this done tonight.
So basically,
All right. Hold on. Zach, shut the up. Get out. We're trying to get the homework done.
Send it to me when you're done.
You bum.
alright, so basically, inverse trig ratios are mainly used to find the angles instead of finding the sides. So, you'd...
So like, hold on. Well, normally you'd use sin to find maybe this side down here. You're using it to find the angle instead.
yeah, you'd use
Okay.
you'd use the inverse of sine to find the angle.
All right. So how do you do it?
So you'd set it up something like this. You put sine to the power of -1,
Okay.
then you put parentheses, then you put whatever the regular ratio is. So opposite over hypotenuse, that's 4/5.
Okay. And that'll help you find the x or this angle.
Yeah, and then you'd set it equal to the angle,
Okay.
x. Then you would just solve for that.
And how would you solve for that? You just plug in sin.
You plug this equation into the calculator,
and the
and that
answer-
would give you 53.13
Okay.
angles, of course.
Okay.
Then you just repeat the process with every other ratio.
Using the right sides.
Yeah, using the appropriate sides.
Okay.
So for cos, you'd set it up as cos to the power of -1. Then you'd set it up as adjacent over hypotenuse, because that's what cos is.
Yeah.
So
Got it.
3/5
Mm-hmm.
equals x.
All right.
So x would equal 53.13 degrees, of course.
Okay.
And then for this one, you'd set it up but with tan. So tan to the power of -1 is opposite over adjacent. So 4/3 equals x.
Wow, the homework Mr. Chang gave us is really easy. They're all the exact same answer.
Exactly. Yeah, I guess that's what he's trying to get at.
I'm a dumbass. How did I know how to do this?
So it would be, so that would be equal to 53.13. What a surprise.
The same exact angle. Okay.
So that's basically how we do this.
All right, cool. Take a picture and send it to me.
Have you seen Ricardo all day? Where is he? No. Here, let me call him.
Oh, God. Yo! Dude, we got more homework. Alright, so... Anyways... we got more assignments this morning, and I was working on it during second period, because I hate history, to be honest with you.
So
And
what,
I
you
didn't
just-
really understand spindle speed.
So you just need help on spindle speed?
Yeah.
Alright.
I know the equation and stuff, but I don't know how to put stuff together.
Alright, all you gotta do is plug in the values into the variables. So you already know that the cutting speed of aluminum is 250, so you just plug that in. 250 times 12 divided by pi times the diameter, which is 0.5.
Okay. Oh man, I'm tired. I didn't get much sleep last night because of all that trig.
Anyways, then you just gotta simplify that. Let me pull out my handy dandy calculator right here.
Oh yeah, I remember the one that you spent $200 on.
Ready. Money well spent. So 250 times 12. It's 3,000 divided by pi times 0.5, which will give us
Hey, you're really good with that thing, huh?
I've had it for a really long time. It'll give us 1909.5 0.86.
Alright, cool. Let me write that answer in real quick in the box. $86? Alright, cool.
Yeah. You know what I just remembered? We also had production rate problems.
Dude, already took care of it. I don't understand all that trig.
That's a pretty nice
I know how to do this.
It's a really nice change.
That was a pretty weird problem. I don't know why he would want us to do.
Assign something that's so like that would give us not really a clean answer.
Yeah, it's kind of weird.
So basically, yeah, you did it all right. That's pretty nice.
I know,
It's nice to know. It's nice to know that you actually know something for now.
Yeah, it was a simple division, dude. I took care of it. Alright, well, I guess we're done for the day. I'll send
Yeah.
these pictures later and I'll send them to you.
Okay.
Oh, dude, I'm so freaking happy we got all that trig done, bro. I'm so tired. I'm ready to go home and just sleep. I have more homework.
our whole weekend's open.
For Endless real.
possibilities.
Dude, we just gotta make sure we get it turned in by midnight. I'm ready to record, guys. What are you talking about?
The video for engineering math.
Wait, we had another assignment?
Yeah, it's due today.
Wait, you're joking, right?
No.
What?